una experiencia muy especial que ha podido reunir a lo largo de su experiencia el papel emergente de los rellenos de pasta para la eliminación segura de relaves. Para quienes no lo conocen, que serán muy pocos, David Stone es ingeniero de minas reconocido internacionalmente en Baking Mines y autor y presentador de talleres en conferencias de backfilling en todo el mundo. Su experiencia abarca todo el aspecto desde el relleno de rocas cementados hasta rellenos hidráulicos y rellenos de pasta. También incluye reología de pasta, así como diseño de operaciones de espesadores, plantas de filtración y sistemas de bombeo para disposición superficial y subterránea. Brinda asesoramiento sobre el diseño y el costo de las plantas de preparación de rellenos y como asesor técnico en varias minas operativas. Entonces, démosle una calurosa bienvenida y un aplauso al doctor David Stone.
Sorry, my Spanish isn't any good, so you don't want to hear me speaking in Spanish. I do apologize. I do want to thank the organizing committee and Alicia for the very kind invite to come and speak with you people today, especially my good friend Emmanuel Pernios, who drugged me into this. So I'm very pleased to be here to talk to you today about mine backfill as a means of providing secure storage for tailings. And I have to thank Rob for making a really good introduction. I can throw half of my slides away now. But no, we're going to actually touch on quite a bit different viewpoint here in my presentation. And it's kind of in three parts. The first part is more kind of talking about the use of tailings in backfill here in Peru. My career has brought me to Peru about 30 years ago. I have a lot of experience here with mine backfills in Peru, working with good companies like Volcan and Dorun, and with a lot of operators here recently. And so a lot of my slides are actually of Peru, and some historical slides of some older operations that go back to the Centramine days. And then I want to kind of focus on how the recent events have kind of shifted the focus on disposal of tailings and how that has put kind of pressure on the new way of getting rid of tailings in the future and trying to maximize the use of backfill. And then I want to spend some time talking to you about how it's changing the regulatory environment, particularly in the U.S., because the U.S. is the only jurisdiction in the world that I know of where they actually have rules about performance and environmental permitting for backfill. You got lots of rules on disposal of tailings for the surface, but there's very few rules about the performance of the backfill underground. Have I got the slides? Yeah, okay. All right, so that's why I say I got my three parts. We'll talk about tailings, talk about the recent events, and then get into kind of this change in the regulatory focus. So backfilling has been utilized here in Peru for hundreds of years. And particularly, since about the 1990s, 1980s, 1990s, hydraulic fill was used pretty much universally everywhere in underground mining here in Peru. Probably the largest accumulation of hydraulic fill operations that I've ever seen in my career, starting with Centramine back in the 80s and 90s, Volcan, Hochschild, Buenaventura, Simsa. And a lot of that had to do because the topography here in Peru doesn't lend itself well to surface disposal in a lot of places, so we're trying to get rid of the tailings as best we can. But also, the other big challenge we have here in Peru is that we have a lot of sulfides in the tailings, and we prefer to put the sulfides back underground than having them sitting on the surface. So With the hydraulic fills, there are some challenges, and Rob kind of touched on it. With hydraulic fill, we end up with a lot of decant water that we have to get rid of. And we can't use whole tailings generally in hydraulic fills. We have to pre-cyclone it to deslime it because we need good percolation rates, good settlement rates when you get that material into the stope. And so we end up with very low fill densities, so your replacement ratio of the percentage of mill tailings that you can put underground is relatively low. The safety of bulkheads can be an issue. A lot of the mines here in Peru are using cut and fill with hydraulic fill, so we're not putting a lot of pressure on the bulkheads. But in other jurisdictions like Australia, they've learned the hard way about trying to fill big stopes with hydraulic fill, and they've had a lot of fatalities related around that. And so with hydraulic fill, it does limit the mining operation because you're very limited in the strength of the fill without having to add a lot of binder. And the other problem is that it's not amenable to underground, mining underneath it, or underhand mining. So this, Rob touched on this, and actually his slide was a really good replacement of mine here. But, the replacement ratio, how much mill tailings you can put underground, people always talk about it being 50 to 60% of the mill tailings. But the reason they think that is because they say, well, we can get a 1.8 per ton density underground, and we got 2.7 tons per cubic meter in situ, that's around 60%. But what they forget is the backfill is mostly water. On a volumetric basis, a hydraulic fill is almost 60% water, and so most of the actual void space is filled by water and not by solids. So if you took a typical gold mill tailing, say a SG around 2.7, if you do the math, you can only get about 42% of that material back underground, and that's on a weight percent basis. If you look at a high SG, and I realize 3.9's a pretty high SG, but we do have operations that have SGs over 4 for the tailings, then your replacement ratio goes up a little bit, it goes down, I should say, because again, what happens is that you have the tailings solids on a weight percent basis, the volume of the water is much greater, and so you get less material underground. So the big push then is to advocate the use of paste, and obviously Rob and I are more or less in the same business here, trying to sell you guys on putting the tailings back underground in the form of a paste. And there's a lot of advantages with doing that, a lot of technical advantages. One of the big things obviously is that we don't have to deal with the decant water. We get a little bit of bleed water out of the tailings, but for the most part, there's no drainage out of the paste. And so we're able to achieve much higher densities in the material that's placed into the stope, and the material remains saturated so we don't have an oxygen environment that promotes this alteration of the sulfides, so we don't generally have the ARD issues. The bulkheads are a lot safer with paste, and we can pour much larger volumes when we're pouring with paste. So it's amenable to bulk mining methods, whereas the hydraulic fill is better suited to kind of a cut and fill type environment. And being able to mine underneath paste is a big issue because it kind of broadens the scope in terms of how the backfill is married to the mining environment. So if we go to that same calculation again now with paste, what we see now is that we can get a much higher proportion of the tailing solids underground. I'm running these calculations at 76% solids, but as Rob mentioned, the solid content for a paste can go anywhere from 68 to 85% solid. So it's sensitive to what your solid content is. But if I pick a generic number of 76, which is kind of a good average number, we're actually achieving about a 10% increase in the percentage of mill tailings that we can put underground, and that makes a big difference. I mean, if you're running a million tons of tailings a year, that's another 100,000 tons of tailings that can be stored underground. So the thing is that one of these. So unfortunately, there are some barriers to the implementation of paste, and most of these barriers are related to the economics, and that's where this kind of change in the stakeholders' expectations and the changes in the regulatory environment really come into play, because they start to mellow out some of these economic benchmarks that are determining the how widespread we have with the application of paste. So we're going to talk about. Whoop, there we go. So, we do have some limitations with paste, and again, Rob kind of caught on some of these. It's not well suited to really small pores, so if you have a very small cut and fill mine, that means you're starting and stopping the backfill plant all the time, and paste plants really don't like that very frequent stopping and starting. We have trouble pumping at long horizontal distances. We have a lot of trouble pumping it uphill. I know there are some projects I visited here in Peru where they've had some terrible problems trying to pump paste uphill. And not all mill tailings will make a good paste. And Rob showed the kind of the typical PSD. Well, if you have a paste that has a lot of fines, I mean, he talked about the 20% passing 20 microns. If you have a mill tailings that's 80% passing 20 microns, then you end up having to basically deslime the tailings before you can make a paste. Otherwise, it's going to make a paste that consumes a lot of cement, and it becomes very expensive. So a lot of times when we have very, very fine grinds, we have to amend the tailings. So the other issue is that, and the big issue, particularly here in Peru, that has really kind of held back the implementation of paste is the economics. And because at the front end of these implementation studies, we're always working out what the NPV is, and these decisions are making purely on an capital and operating cost basis without really kind of having a consideration of what the impact is to taking those extra tailings and putting them out on the surface, and what happens if we have a problem with the surface disposal. So another big problem we have is that even though the technology for filtration has evolved a lot, particularly in the last 10 years, we're still limited in terms of the capacity of filter plants. And a lot of times we end up having very, very large, very expensive filter plants in order to support the use of tailings. And more, I would say that more than 50% of the tailings paste projects that we get, it's in conjunction with a dry stack. So that immediately means that they want to use pressure filtered tailings, whereas in paste we prefer to use vacuum filtered tailings because we have problems with that come with pressure filtered tailings. So these limitations in the capacity of the filter plants can be a really expensive issue. There is a limitation in capacity of a paste plant as well. So, in the past we talked about paste plants that were 800, 1,200, 1,500, 2,000 tons per day. But nowadays, people want to talk about paste plants that'll do 20, 30,000 tons per day. And there we start running into capacity problems with the equipment, and basically it means that you end up building multiple plants. A lot of times, in order to implement paste, you're going to have to change the mining method, or at least make some modifications to the mining method. But a lot of those changes are actually good because what they do is they result in faster stope turnaround times, so which means that you can increase your throughput. So it's actually more efficient mining it with paste. So the big issue in the past, as I say, when they were when we were evaluating these paste plants is that we started off in the 1990s building paste plants for around 6 to 7 million. And then for some reason, when we got into the 2000s, the cost started jumping up into the 10 to 20 million range, and nowadays we talk about paste plants that are, north of 20 million and even upwards of $50 million. And that's a very large investment, because if you're talking about comparing that to a wet tailings pond for disposal of tailings, 50 million, you can build an awful nice tailings pond for $50 million. But what the $50 million investment in paste does is it gives you that security, because we don't have the risks of putting the tailings out on the surface. And so, unfortunately, that kind of takes us into the next topics then so some of the issues that we're going to face when we implement the paste is that with hydraulic fill, we know we have problems with acid drainage, because as soon as the hydraulic fill drains, it sucks oxygen into the tailings, and if you've got a lot of pyrite and sulfides in there, those pyrites and sulfides are going to oxidize, and you're going to get acid drainage. So theoretically, with paste, it remains saturated for forever, and because we have that saturation, we don't have the oxygen contact with the sulfides, and that then prevents these ARD reactions from taking place. So that's why a lot of times we end up getting told that, well, we're going to do a pyrite separation at the end of our flotation circuit. You get to get rid of the pyrite tailings, and we'll take all the clean tailings and put them out on the surface. And that makes a lot of sense. And a lot, we have operations that are operating here in Peru where they have, upwards of 80% pyrite in the tailings. So the tailings is just about nothing but pyrite. So on the other side of the coin is we do have issues with sulfates in paste, and generally the sulfates are coming from the mill. So if you're doing liberation of metals in a high sulfides ore, generally there's sulfates will get introduced into the circuit in the mill, and that then is the carrier water that brings the solids to the paste plant. So you end up with a lot of sulfides in the paste, in the water in the paste, in the matrix. And what happens is that when you get to a sulfate level in excess of about 2,500 ppm, the sulfates will react with the calcium in the cement and produces a form of gypsum called etrogite. And that material is expansive, and when it expands in the void space in the paste, it basically breaks all the cement bonds. So what you see is that you have a very strong paste initially, and then over time, after about 28 days, it starts to lose strength. And in some cases, I've seen it where you can lose upwards of 90% of your strength. So if you need a 1 MPa backfill, after about 3 months, you've basically got a 100 kPa backfill. Can be a huge problem, because when you go to mine the secondary stope, you don't have enough strength to carry that stope, and the material can slough into the secondary and produce dilution. But there's a lot of debate about this, because what we see is we're doing all the measurements on laboratory prepared samples, and they're being cured in the laboratory, and a lot of times they'll strip the molds, and you can see here in the top picture where they take the molds, take the samples out of the molds, and they leave them sitting in the air, and then what happens is the sulfides are oxidizing, and you're producing sulfates, and when you put that sample in the machine, you get one of two things. In some cases, you get incredibly strong samples, unrealistically strong samples, and in some cases you get this degradation that you see because of the oxide reactions. So there are some issues around that we always investigate when we're doing new projects. So I want to talk about some of the recent events, and my purpose here is not to focus on the events themselves. I think there's been more than enough said about that. But what I want to do is focus on how it's changed the perceptions in the industry, and it's changed the whole regulatory focus, and basically, to put it in a nutshell, it's kind of scared the pants off the regulators. And so it has had a big impact on the mine backfill business, because projects that were considered unsuitable for backfilling or unsuitable for paste in the past all of a sudden now present themselves as being, well, I don't care how you do it, but you need to get the tailings underground. We need to get rid of as much tailings as we can. And it really comes down to, obviously the economics. You see that, Mount Poly, they're talking about $500 million to clean up Mount Poly. Well, that's a lot of paste plant for $500 million. And then, of course, not to irritate anybody, but we have the events in Brazil. And now we're talking about some really big numbers. Their stock lost $19 billion, the 250 real fine from the state of Brazil, with $150 million in cleanup costs, and cleanup costs in the billions. And of course, immediately in Brazil, resulted in some regulatory changes. Yeah, this slide thing does not work. So you see these regulatory changes right away. When they say, well, self-regulation is not working. We need some sort of external, regulation system to keep track of these things, because the mining industry can't look after itself. We have a lot of calls for creating international standards, but, having some sort of a Bible that you have to follow. Of course, all of this is all for surface disposal. It doesn't affect us in the paste business. We're immune to all those regulations. So, at the end of the day, I think that the couple of big takeaways here, one is the comment that, the unintended consequence of Mount Poly was the quick reaction by Alaska, First Nations, and activist groups who united to condemn mining. And the second thing was that the failure of a well-engineered facility run by a reputable company in a first-world jurisdiction with regulatory oversight unsettled many and provided all the ammunition that was needed for activists and NGO groups to fight against mining projects. And it really has hurt the mining business, particularly visible in Canada and now in Brazil. And now you have the state of Alaska saying that they want to be involved in permitting of projects in British Columbia. Well, how does that make sense? I mean, but that's the problem. So we have this whole kind of different focus now in the regulatory environment. And part of that regulatory focus is that, they're pushing for all tailings should be dry stacked. I mean, that's kind of the message that they're pushing towards. But the problem is that not all tailings are suited to dry stacking. There are some limitations. But, if you look at it on an economic basis, you say, well, why would you invest in a paste plant? Because, even dry stacking is cheaper than paste. And we'll just put all the tailings in a dry stack. Why would we put them spend all that money building a paste plant and put the tailings underground? But I think it really comes down to it is particularly a sensitive project thing here in Peru, because with the topography that you have here and the high sulfide tailings, you have a lot of limitations here in terms of the site constraints, where a paste system is immune to the weather. It's immune to the rainfall, it's immune to the topography, the terrain, and we can deal with high sulfide tailings in paste. So it really has a much more widespread use than trying to dry stack, and at the end of the day, it's probably going to end up being cheaper anyway. But there's a lot of jurisdictions that are now really trying to force the whole concept of dry stack tailings down the mining industry's throat as being the solution for tailings disposal. So, so we have lots of changes that are coming through in the regulatory environment now. And so, prior to 2008, all the regulators cared about really was that the backfill would be stable. They did not get involved in the actual permitting of the material that you're putting underground. But starting with the rodeo paste plant that was built in Nevada back in 2014 or 13, somewhere around there, all of a sudden the regulators started looking at the material that was going underground. And prior to 2008, we had this kind of global image that paste has got cement in it, so it will buffer any ARD issues. You'll never get ERD issues. The paste is always going to remain saturated, so you can't have oxidation or alteration. The paste is very low permeability, so you can't leach any metals out of it because it would be a very, very slow release. And that at the end of the mine is going to become flooded, and therefore you couldn't have a more stable place to put the tailings than to put it back into the stove. And as Rob said in his presentation, we're just putting back the material that came out of there in the first place. But after rodeo, and in particular with some of these events that are taking place now, we're not able to fool the regulators in the U.S. that way anymore. And so the U.S. is the only jurisdiction I know of that has a regulatory environment right now around the permitting of paste projects. And I would anticipate that, generally when these things happen in the U.S., then they end up migrating around the world. So we now have a regulatory environment in the U.S. that requires us to do certain things in order to permit a paste project. And of course, it all comes down to the geochemical stability of the paste. And I saw somebody popped a question up after Rob's thing about whether the cement causes any issues with groundwater. And it really comes down to the whole geochemical stability of the paste itself. What impact is it going to have on the groundwater? Do you get metal leaching? Are you going to get metal releases? And then the one question that we've never been able to answer is, how long does paste last for? Because, the earliest paste plants go back to about 1997, so we're about 30 years of paste. So who knows? I don't know if it lasts for 100 years or 200 years or whatever, but that's a really big kind of unknown right now is a paste underground stable for 200 years? And so we see a lot of regulation coming now. One of the things is that we have, good grief, we have this mandated environmental testing. So every paste project in the US now has to go through this sequence of testing, looking at the mineralogy, looking at the acid-base accounting, doing passive diffusion testing, and doing the active leaching test. It's a dynamic active leach test. And so rodeo was the first paste plant that had to go through that process, but every paste plant that's being permitted since then is now having to go through this same process. So, and the other thing, of course, is cyanide. So, you mentioned cyanide to the U.S. regulators, and their eyeballs go all buggy. So, which is ironic because the Pogo paste plant in Alaska was built a long time ago, and it uses cyanide tails. But when they got around to that at rodeo, they got a little bit more concerned, probably because it's a different state. But we have lots of paste plants that use cyanide tailings. There's nothing wrong with putting cyanide tailings, and you can see a kind of a list of projects in my slide there that go through all the projects that are using cyanide and tailings these days. And basically, we have some testing that we have to do. In the U.S., the limit is a 10 ppm wad cyanide content is the release. So what they do is they put the paste sample in a wet cell, and they leach water through it, and the leachate coming out the bottom can't exceed 10 ppm wad cyanide. And that usually goes into the permit then, so it becomes a permit condition for operating the paste plant. They have to take samples from the paste and do wad cyanide testing on it. In Australia, they allow 50 ppm wad cyanide. And then in the U.S., we use this ASTM D2036 is the standard that they use for measuring cyanide in the paste. So the other thing then is the metal leaching. Good grief. And so the point I make here is just that if you look at just a regular migration through permeability or percolation or whatever it is, with a paste, it takes 32 years for it to migrate from the center of a 20-meter stope. So it's very low. But what's happening is now that they're doing this diffusion testing, they're finding that it's the diffusion that migrates the metals, not hydraulic conductivity. And that's a whole different ballgame. Good grief. All right, and I'm not going to go through the consolidation issue here, but again, we do have to deal with consolidation with paste because it's a very long-term issue. So what I want to do is get to my last slide here, if it'll get there. Okay, so this is my last slide. Okay, so we have this new reality, okay? And the new reality is that the stakeholders want to be involved. We have a mandate now where we need to put as much tailings underground as we can. And because of when you factor in the cost that we're facing with some of these failures in Brazil and Canada and places like that, really the cost of the paste plant now is almost irrelevant because the downside of not putting the paste in there is a very, very large number. So my takeaway from this is that I'm not a big believer on dry stacking as the solution for surface disposal, and that's not even in my in my wheelhouse, talking about surface disposal. But a lot of times we're forced to pair dry stacking with paste, and that is a good solution in most cases. So, all right, and I've got this end off with this picture of me taken yesterday, and oh, thank you for your questions. Are they in English? Strength in particular. So the strength of the backfill is governed by your stope geometry. So it's the geometry of the exposure. And it can be, if you're overhand mining, it's probably going to be somewhere around 200 kPa. If you're underhand mining, it could be upwards of 4 MPa. Maybe as low as 500 kPa, but up to 4 MPa. It depends on how that backfill is being exposed. The elasticity is a really interesting question, and I flipped over the consolidation slide because we're actually seeing now in some of the projects that we're doing in Europe where they're forcing us to do these one-dimensional consolidation tests where we're measuring the elasticity in the fills. But generally, a paste fill would have a modulus of elasticity from anywhere from about 200 MPa up to about 500 MPa. If you have an incredibly strong fill, like a 4 MPa compressive strength, you've probably got something closer to a 1 GPa elasticity for your backfill. So the question too about pumping up. So the problem that we have with pumping up with paste is it segregates. And so what happens is we have this issue with what's called laminar flow settling, where the high-density solids will tend to sink to the bottom of the pipe. And as soon as you stop pumping, you end up with this plug at the pump. And it causes a lot of wear on the pump. So even right now, the highest vertical pump that I know of is around 140 meters. I know, Chris, you'd be able to answer that one a lot better. But generally, the rule of thumb that I follow is that we can't go more than 100 meters vertical. You're going to have to build booster stations to pump it up higher vertically. Yeah, so on the commingling, there's a lot of paste plants where we do commingling, especially if we have waste rock that's pegged waste rock, is crushing that up and adding it into the paste. At Leeville, their permit, because their tailings were considered to be potentially acid generating, their permit requires them to add 25% by weight crushed limestone into the paste as a buffer to generating ARD in the paste. So I think the commingling is a very good idea. There are some technical advantages to commingling from a paste plant operations side as well. So it is a very good strategy. The cost of mine closure, I don't know how to answer that question for how that relates to paste. I don't know anybody that's looked at using biocides or detergents or anything like that for tailings. I'm sure there's probably some additives that can be added in there to, in particular for tailings that are potentially acid generating, to try and maybe buffer those types of reactions. To say, you know, the solution for paste was always just add more cement. In some cases, we actually add quicklime as basically as a sacrificial buffer to try and buffer the tailings if we're using it in paste. If you want to know about quality control, send me an email. I've written a couple of papers on quality control. I just submitted a paper for the Minefield 2020 conference, which is going to be in Poland next year. And I have a paper in there on paste quality control, but I've written other papers on paste quality control. That's a subject that I get involved a lot in. Okay.
Thank you.